So today we have Prashant Pandey here with us, who I might have butchered your last name. I apologize. I always just call you Prashant. The student at Stony Brook, working with Michael Bender and Rob Johnson still, and he's worked on a lot of like sort of integration of like system stuff and algorithmic stuff. So he's done like cryptographic file systems. He's done a bunch of stuff with fixing errors in DNA. That's what he's going to talk to us about today. So we're going to data structures that we can use for representing like K-more graphs, and he's going to explain more than I'm going to be able to explain it. But I think it's kind of interesting stuff. And I especially like the idea of what kind of algorithms can you do in a compressed graph. I think that's kind of an interesting question. So Prashant, take it away.
All right, so today I'm going to tell you about deBGR. So deBGR is an efficient and a near exact representation of a weighted DeBruijn graph. So in the talk, I'm going to tell you at a high level that's what is a DeBruijn graph and how it is used in the field of computational biology. And so what are the issues with those kind of graphs? And then we'll see how we can represent these graphs that are very, very huge in a very small amount of space efficiently and do error correction as well on them. So let's start the talk by talking about DeBruijn graphs. So DeBruijn graphs are ubiquitous in the field of computational biology. They were introduced in 2001 in this field by Webster et al. And then since then, they have been used in many different applications across the field. The input in computational biology is raw sequencing data. It comes in the form of strings of DNA bases, and there's slots of them. And all this input data, the raw sequencing data, is first converted into a DeBruijn graph representation, and then later on it is used in many different applications in the field, like a sequence search and transcriptome assembly, genome assembly, and also reads error correction. So in short, a DeBruijn graph is a data representation at the heart of a lot of sequence analysis. So let's see what does a DeBruijn graph looks like. So DeBruijn graph in computational biology is a subset of the actual DeBruijn graph in the math, wherein there's an edge, which is a string of length k, and the edge, or the k-length string, it connects its two k-1 substrings in the graph. For example, in this case, the edge is a string of length 5, which is over the alphabet 0 and 1, and it is connecting its two k-1 substrings. So the 0010 is on the left, and 0101 is on the right. So that's pretty much how a DeBruijn graph looks like.
So are all the nodes of length k-1?
Yeah. So when you create a DeBruijn graph, you first decide how long the edges are going to be, and all the nodes are k-1. Also, I want to make this clear that in this talk, we're going to use this definition here, which is the lengths or the edges are of length k and the nodes are of length k-1. But there are different applications where they use vice versa, where they create all these nodes that are of length k and the edges are of length k+1 and so on. So, but we're going to use the edge-centric definition of the graph in this talk.
And are you going to be having all 2 to the k-1 possible nodes, or is it going to be a subset of that?
Oh, that's a good question. So when you talk about a DeBruijn graph in math, then yes, you have all the exhaustive, all the possible nodes in the graph. But in the computational biology, these input, these edges are coming from the input data set. So now they're not exhaustive. So they're all the distinct edges that are present in the input data set. You build that graph on top of it. So you may not always have all the possible combinations.
And the edges are only between pairs that have the property that you can prefix one to the other?
Yes, exactly. So you can see that these nodes, these nodes are of length k-1, that is 0010 and 0101. So they always share a prefix of length k-1 between them and so on. So that's the way you actually create this graph out of the input data set. So as an example, in computational biology, the input data is present in the form of reads. And a read is actually a string of bases over the DNA alphabet. So in this example, you can see this is a read, which is a DNA alphabet, and it's a string. And from all those reads, we actually extract k-mers. And where a k-mer is a substring of length k. And we extract k-mers using a sliding window. So here we are extracting k-mers of length 5. So we first take the first 5 bases, and then we do the right shift by one position, and then we extract the next k-mer and so on. So the input data is in the form of reads, and then we extract the k-mers, and then we use these k-mers to build this DeBruijn graph. And these k-mers acts as edges in the DeBruijn graph. So to see a complete example, in this case, you can see there are 2 reads, and we extract k-mers of length 5 from these reads. And so there are only 3 distinct k-mers in this the input data set here, and then we build this graph on top of it. So you can see, for example, in this case, this edge AAAT, it connects nodes AAA that is of length 4, which is a k-1 prefix of this particular edge, and the other node on the right is again a k-1 substring of that edge, and so on. So that's a very simple DeBruijn graph.
So I have a question.
Yeah.
So potentially we could also connect like the first node on the left and some of the nodes from the right.
Yeah, sure.
Yeah,
so
but we
loops as well.
But we don't do this because they are not adjacent in the input.
No. So once you have extracted all the k-mers, then you don't have information about the positions of these k-mers in the actual input data set. So in the graph, you can connect anything possible. So even if there could be loops, there could be nodes across different places in the actual input data set, they can be connected in the graph. Because once you have extracted k-mers, then you don't have this information about where they're actually present in the input data set. So you just take these k-mers like edges in the graph, and then you represent this graph whichever way possible. So the rule is, if 2 nodes, they share a k-1 like string, then they will have an edge in between them. That's pretty much the rule there.
But you only take the edges which are present in the input.
Yes. So edges comes from the input data set, of course. Yeah.
I guess the question is, so you had five mers here that define these edges.
Yeah.
I think you're saying that if there were a string CAAC in the input, you definitely put an edge from that left node to the right bottom. Question is, if CAAC was not in your input, do you still put that edge or not?
No, if the edge wasn't there, then there won't be, because, okay, so here in this case, since we are taking the edges from the input, then if there's no edge, then then there's no k-mer in the input, then there won't be an edge. But if we take nodes as an input, then you would do that edge as well. But here in this case,
is it because you want to then find just the coding of the entire sequence? What is the sequence? Is it because essentially all the k-mers are shuffled around, and then you want to get like only a line of this?
Yeah, so that's exactly what the motivation of this DeBruijn graph is. So the problem here is that in biology, you have these long like genomes, which are like very long strings. And for a human, it's the length of the genome is like 4 billion bases. But when an instrument reads that, it reads that genome in parts. And so what the issue is, now you have some multiple reads, and these reads are the parts of the genome. So you have to align them together to form the actual genome back. So basically in this example, you can see we have some multiple reads, and you build this DeBruijn graph on using those reads. And now what we do is that in a typical assembly process in which you have to construct the whole genome back from this input data set. So what you do is that you traverse this graph, or like walk along the path in this graph. And what you do is that all non-branching paths in the graph, they are also called as contigs, and you output those, and then they are used in downstream applications to actually glue them together to build the final genome. In this talk, I'm not going to go into the details of how they glue these together, because they use different kind of algorithms, and they have some heuristics as well to glue these together to find the final genome. But the motivation is that you have input data set, you represent it in the form of a DeBruijn graph, and then you walk this DeBruijn graph to find all the non-branching paths, which are then used to actually form the final genome. And these non-branching paths, we do that because these non-branching paths across reads, they actually represent some part of the actual genome. So in this case, you can see there, like the genome is there, and all these non-branching paths, like in these colors, like orange or like blue, they represent some part of the actual genome. So we can glue them together to form the actual genome back. So the motivation is that, again, so you have this graph, you walk it, traverse it, and then you create the genome back. So this is only one of the applications in computational biology. There are so many different applications where they use this graph. So when you talk about assembling a genome, then only a DeBruijn graph that has the topological information works well. However, there are many different applications wherein you need much more information than just the topology of the DeBruijn graph. For example, there's a kind of application known as transcriptome assembly, wherein they deal with data set like RNA data set from multiple different species in a single graph. And the graphs tend to be more complicated in those cases. And also when the instruments read those the RNA from the actual organism, they don't read it with an equal coverage. So they read it for some parts very efficiently and some parts not very efficiently. So they really need the abundance information in the graph. From that I mean, they don't just want a DeBruijn graph, but they also want the information about how many times or what is the abundance of each edge is there in the input data set. And for that kind of use cases, we have a weighted DeBruijn graph. So a weighted DeBruijn graph is similar to in topology to a DeBruijn graph. However, now with each edge, you have the abundance of that edge in the underlying data set attached to it. So in the same example, we have two reads here. However, you can see the edge CAAA appears twice across different reads. So its abundance is 2 and it is attached to it in the graph. So this is a typical weighted DeBruijn graph. And the challenge here is that now with the graph, you have to also store the weights or the abundance of each edge in the graph. And later in this talk, I'm going to tell you that even though storing extra information is an obligation, but it's also an opportunity at the same time. I'm going to tell you that how we exploit to our advantage the available information in the form of weights in the graph. Okay. Moving on, so we have talked about DeBruijn graphs, how they're used in the field, and what are weighted DeBruijn graphs and why they're needed. Now, the big issue here is that the space usage of weighted DeBruijn graph. So DeBruijn graphs, they store only k-mers. And so the memory usage of the representation of a weighted DeBruijn graph, it scales linearly with the number of unique k-mers in a data set. For example, to represent a weighted DeBruijn graph of a human genome that has few billion distinct k-mers in the input data set, the state-of-the-art system takes something around 100 gigs of space. But when you go to transcriptomic assembly, and they use the metagenomes, and for example, if you take the metagenome of soil, wherein you have millions of different species in a single data set, then the amount of space that the state-of-the-art system takes to represent the weighted DeBruijn graph is of the order of few terabytes. So like researchers in the past, they have been using beefy server machines and testers to actually do the analysis on these huge data sets and the graphs that they create out of these data sets. So like to represent these graphs compactly is a big issue now, that if you don't want to go to some multiple different machines, and if you want to do the analysis on a single machine, then one thing is that you want to represent these graphs as compactly as you can. So to this end, in this talk, I'm going to tell you about compact representation of the weighted DeBruijn graph. And a compact representation, as I said earlier, it would enable to do the transcriptomic assembly on machines with very less amount of resources. And it would also enable you to assemble some of the fundamentally large data sets that were not possible to assemble on a single machine before, because the data sets and the size of the representation was very huge. That's where you needed some multiple machines to store the data and do some other kind of tricks. But if you can store them compactly, then you can store them on a single machine and still do all the analysis. Now we'll go in the second part of the talk. They will start to talk about how do we actually represent a DeBruijn graph or a weighted DeBruijn graph. And to start off, we'll first talk about the past work, that how they did some work to actually represent the DeBruijn graph compactly, and we'll know about the tricks, and then we'll talk about representing a weighted DeBruijn graph compactly. So to start off by representing a DeBruijn graph, so on your right-hand side, you have a DeBruijn graph where you have some edges and the nodes, and the edges are coming from the input data set. And since a DeBruijn graph has these edges, we can represent a DeBruijn graph as a set of all these edges. And all we need to do in the graph is that we want to traverse the graph. So we can do that by storing only the set of edges. Because if we want to find out what are the neighboring edges of a given edge are, so what you do is that you just shift the given edge by one base, and you append all the 4 possibilities of the bases, and then you query for all those possibilities. And if you find any of those edges are there, then you know that how to go forward in the graph, and you can find all those paths. So to represent a DeBruijn graph, all you need to do is that only represent all these edges in a set. And since the number of distinct edges or the elements in the set are huge given the data set or the input data set, one way to reduce the space of the representation is to actually store the set compactly. And one way to store the set so compactly is using an approximate set representation. And to do that, we have these approximate membership query data structures. An AMQ data structure supports two kinds of operations. You can insert an element, and you can also query for the existence of a given element in the set representation. AMQ is a lossy representation of a set, and it is often very compact. But the space savings comes from the fact that it occasionally returns a false positives to your queries. From that, I mean, occasionally when you query for an element X in the set, it may say yes, that this element is there, even though that element is actually not present in the set. So that's a false positive query or an answer. The most commonly known or commonly used AMQ data structure is a Bloom filter. And I guess it's used across different fields in computer science. And yeah. So obviously, Spell et al. In 2012 first showed that how you can actually represent a DeBruijn graph using a Bloom filter. However, since Bloom filter is an approximate representation of a set, the graph that you will get when you use a Bloom filter to represent a set is not the exact graph. And you will tend to see some errors. And all these errors are the topological errors in the graph. And these appear because, in the graph, you can see the nodes and the edges in the green are coming from the actual input data set. But the nodes and the edges in the red are introduced in the graph because of the errors in the Bloom filter. And these appear because, for example, if you are at a node, if you are at an edge, say CCGA, and you want to find out if there's any neighboring edge on the right-hand side of this particular edge. So what you do is that you shift that the edge by one base on the left, and you get CGA. You append 4 different bases to it, and you try to query for that edge now. And the edge you get is maybe C, G, A, and G. And if you query for that edge, even though that edge doesn't exist in the input data set, it is present in the set because now you're representing the set as a Bloom filter. So now you will find a false path in your graph and some false nodes in the graph as well. When you represent DeBruijn graph using a Bloom filter and you traverse that graph, then you would end up seeing some extra false edges in the graph. One of the results in the paper was that if the error rate of the Bloom filter is less than some percentage, say 1%, then the overall structure of the graph is still intact. And this comes from the fact that if in your graph you have 2 components that are far apart, and then there's very small possibility that 2 distinct components or edges in the graph would have a path in between them that is a false path. Because to connect 2 different k-mers with a path length of say 4, the probability of that is very small because it will be a multiplicative probability. So if the error rate of the graph is in general 1%, so to have a path, have false paths between 2 k-mers or 2 edges will be 1 over 100 to the power 4, so which is already very small. So one of the results they showed empirically is that they created they had a bunch of graphs where they had a structure of the graph, and they inserted all the elements of that graph in the Bloom filter, and they tried to traverse the graph using the Bloom filter, and they ended up with the same shape of the actual graph. So the error rate was small, so the overall structure of the graph doesn't change much.
What do you mean the connected components don't change?
Yeah. So one of the results on the graph in the paper was that they had a big graph, which was a big circle actually. So the structure was a big circle. And now once they inserted that graph in the Bloom filter and they tried to traverse it, they did find some false paths, but the false paths, they were not very long. They die off very soon after 2 or 3 hops. So the overall structure of the graph would still remain the same. You would see some tweaks here and there when you do the path length traversal, but otherwise the overall structure would still remain the same. That was one of the results. And even though this is an approximate data structure, most applications in computational biology, they want an exact representation of the graph for their analysis. So it was a starting work, but it's not so getting used in so many of the applications in CompBio because they still need an exact representation. So building on top of this work, Spello et al. In 2016, they showed that you can actually exploit some inherent redundancy in the input data set to actually reduce the error rate of the Bloom filter without increasing the space usage. So what they showed is that there's a very high chance that every k-mer will have its adjacent k-mers also there in the set. So what you can do is that if you query for a given k-mer in the Bloom filter, and the Bloom filter says yes, and if both its adjacent k-mers are also there in the set, then there's a very high chance that that k-mer is not a false positive answer. However, on the other hand, if you query for a k-mer or an edge, and the Bloom filter says yes, and if none of its adjacent k-mers are there in the set, then there's a very high chance that it is actually a false k-mer. So in this example, you can see, so before there was an edge AAAT in the set because it was there in the Bloom filter, even though it was not there in the input data set. Now, if you query for adjacent edges of that particular edge, so none of them are there in the actual Bloom filter. So you can say that with a very high confidence that that edge is actually a false k-mer and not a real k-mer. So if we just do some extra queries in your data set, you can weed out a lot of false k-mers from your Bloom filter.
Well, why do you get rid of AGT and not TCC?
Yeah, I'm coming to that. So that is because here you can see this edge is GAGT, right? So you can see if you look for a right neighbor of that edge, there's no right neighbor like AGT or something like that. So there's no right edge or the neighbor of that edge, but there's a left k-mer of that edge there. So what you can do is that you can have different kind of rules in your algorithm. So you can have a strict rule that to make sure that any k-mer is actually real k-mer, both of its adjacent k-mers have to be there in the set. So in this case, only one of its neighbor is there, so you can say it's a false k-mer. However, then you can question me that there could be a real k-mer or an edge in the data set that actually only has its only right edge or a neighbor of it because it could be at the start of a read. So it won't have any of its left neighbor. So what they do is that in that case, they store some extra exact information. And that extra exact information is how many times an edge appears at the start or the end of a read. So if this edge appears at the start of a read, then even if it doesn't have a left neighbor, they are still okay. And if something appears at the end of a read, even if it doesn't have right neighbor, it is still okay. But for everything else, if something is there in the data set, it must have all of its, both of its right and the left neighbor in the graph, in the set, so as to be not a false positive k-mer.
So in that case, you're storing something outside the Bloom filter,
yes,
saying that for this particular k-mer.
Yeah. So, and they can do it when they actually insert everything in the data set. So there, when they go through each and every read, they can store that information there itself. And there's some exact information there.
But the number of reads is pretty tiny compared to the amount of data in one read.
So I can give you exact numbers. So we have done our experiments with a bunch of data sets, and to our knowledge, the amount of information you need to store this thing, the information about the start and end of reads, is about 10 to 20% of the actual data set. So it's very it's not very big. But it's a cool trick, and we're going to use some of these tricks in our work as well. So moving on, in 2013, so Chicky and Rix and Salikov, they showed how you can convert this approximate representation into an exact one. But they did it only for a specific use case, and the use case that you can only traverse this graph, and you can't query randomly in the graph. And the insight they had is, once you're traversing this graph and you don't want to go on any false paths, so all you need to do is that remember all those edges that are directly connected to the actual graph. From that I mean, in this graph, if you are trying to traverse this graph, all those green nodes and edges are the real nodes and edges. And if you want to not go on any of the false paths, all you need to remember is two edges that are directly connected to the actual graph. And as soon as you see those edges, you can stop your traversal on that particular path. So just by remembering a small subset of all the false k-mers in your graph, you can stop going on any of the false paths, and you can say that when you traverse this graph, you will always have all the exact answers, and you will so never go on to a false path. And they call these false schemers as the critical false schemers, because these schemers or edges are directly connected to the actual graph. Is that not clear?
So they're going like a complete traverse of the graph in the approximate data structure, and they see each time they traverse by keeping also the original data structure, and they see each time they traverse one of these.
No, so what they do is that they use a two-phase algorithm to do this. So in the first phase, they go through all of the data, and they insert everything in the Bloom filter, and they build this Bloom filter. Okay, now this Bloom filter, they're going to use it to actually traverse the graph. So what you would end up doing is that anything that is present in the data set, you will query for 4 of its adjacent k-mers on the right and 4 of its adjacent k-mers on the left. So the number of queries you can do in this graph to traverse it is very limited. So if you know all the distinct k-mers that are there in your data set, you can find all those queries you might end up doing. And if you have all those queries, you can do another pass on your data set and find out all critical k-mers, that are the critical false k-mers that are directly connected to your actual graph. And then they can store that small amount of information in RAM. They don't need to read their data back again. So they just do a 2-pass like algorithm on the data, which is stored on disk. And then they store this small amount of information, the Bloom filter, and this small exact data structure of the critical false k-mers in RAM. And then they can say that they have an exact representation as far as the traversal is concerned.
Okay, just to restate what a critical false positive, this is the first edge that went wrong.
Yes, the first edge that went wrong in your traversal, yeah.
And so by traversing the Bloom filter version of the graph,
Bloom filter version of the graph, yeah.
So they know all possible things that might be that first possible thing, and then they're on the second pass, they're checking to see if any of those actually existed in the original data.
Yeah.
But how are they? Given that this whole thing isn't fitting in memory, like how are they?
They do a streaming, so they do it otherwise. So that's once they build the Bloom filter, then they find out all the possible like queries they can do, and they build a set of that, and then they do second pass in their on the data set, and they find if this k-mer is there in this set or not. And at the end of the day, when they have gone through all the data again, they would know that which of the k-mers are there in this set, but not in the input set. So they would know everything that is directly connected to their graph, which is like a false k-mer.
But that one may also take some non-trivial data structures.
Yeah, but it's like temporary. They don't need to store it for permanently.
Got it.
So I'm telling you about this work especially because so one thing to note here is that the kind of guarantees for exactness they can give is only when you want to traverse this graph. And to do that, you must need one seed k-mer from each connected component in the graph, because otherwise you can't start your search or like the traversal. However, they don't have any guarantees if you randomly query for a given k-mer in the graph. For example, here you could see that using this technique of like redundancy, they could remove this k-mer as a false k-mer, because they know that none of its neighboring edges are there in the graph, so they can say that it's a false k-mer. However, in this case, since that edge is not directly connected to their graph, they don't have any guarantees if you query for that particular edge, if it is a false or not. So even though this is exact for a very constrained case in which you only can traverse the graph, and then only it is exact. Otherwise, it is not exact. So they are not exact for a membership query kind of a representation. So which is an important point. So these are the 3 kind of past work where people have used Bloom filters to actually like represent a DeBruijn graph compactly, and did some tricks to either make them exact or like reduce the error rate of the Bloom filter. We're going to use some of these tricks and take them to their logical conclusions to actually represent a weighted DeBruijn graph approximately and compactly and exactly as well. So now let's go and talk about how do you represent a weighted DeBruijn graph. So a weighted DeBruijn graph is similar to a DeBruijn graph, but now you have abundance attached to each edge in the graph. So instead of a set, now you need a multiset to represent a weighted DeBruijn graph. So in the multiset, I mean you have the edges, and you have the abundance of each edge in that graph attached to it. So similarly, or analogous to like representing a set compactly, then you need an AMQ data structure. So to like represent multiset compactly and approximately, you can use a counting filter data structure. So counting filter data structure is a generalization of an AMQ data structure. It supports 3 operations. You can insert an element, you can also delete an element, and you can query for the count of a given element. Similar, analogous to an AMQ data structure, a counting filter is a lossy representation of the multiset. As you had false positives in an AMQ data structure, you have overcounts in this kind of a data structure. From overcounts, I mean, whenever you query for the count of a given element, at times it might result in an overcount, but it will never return in an undercount. So the errors are always one-sided in this counting filter data structure. Commonly known counting filter data structure is a counting Bloom filter, but there are a lot of issues with the counting Bloom filter to use for a very skewed kind of data set. I'm not going to go deep explaining those issues, but I just want to point out here is that the state-of-the-art counting filter data structure is a counting quotient filter. It is like our work. It appeared earlier this year at SIGMOD. And so it is a state-of-the-art data structure. It is very good for skewed kind of distributions. And I'm saying skewed because all of these real-life data sets, these graphs and the multisets for the graphs, they are all very skewed. Few of the k-mers are going to appear a million times, and others will appear only once or twice, and so on. So there's a very skewed distribution of the abundance. And so again, earlier this year, we had another paper at bioinformatics where we showed that you can actually use a counting filter data structure to represent a weighted DeBruijn graph approximately, and using a very small amount of space. However, one thing to note here is that now, along with the topological errors, as you had already seen in a DeBruijn graph or the approximate representation of a DeBruijn graph, now we have abundance errors as well. So abundance error appear in your set when 2 elements or the edges in your input data set that do exist in your input data set, they collide with each other, and they give they result in the overcount of both the edges. For example, the actual weights of so the actual weight here for this edge is 2, and this edge is also 2. But when you represent this using a counting filter data structure, what happens is that they could collide with each other, and they can result in an overcount for both the edges. And so now we have 2 kinds of errors: abundance errors and the topological errors when you have an approximate representation of a weighted DeBruijn graph. And now the challenge here is that we want to get rid of all these errors in the approximate representation of the weighted DeBruijn graph. So in this paper, debugger, we have an algorithm that uses the counts in the approximate representation in an counting filter data structure to iteratively self-correct all the approximation errors. It corrects both kind of errors, abundance errors and the topological errors in the graph. And also we give higher guarantees in terms of the structure of the graph, because now we not only support traversal queries, but we also support membership queries. So with a good confidence or with a high confidence, we can say that you can query for any k-mer in your data set or from the universe, and we can say if that k-mer is actually there in the site or not. And doing all this, debugger takes only 18 to 28% extra space compared to the approximate representation, and has no empirical errors in the representation. So now we're going to see how we do that. So we do this. So in debugger, we use a simple weighted DeBruijn graph invariant. And the invariant says that the total incoming abundance at any node is equal to total outgoing abundance of that node. So in this graph, you can see the bold blue line is the path of the read in the graph. So there are 2 reads coming in at node AAAA, and there are 2 reads going out. So the total incoming abundance is actually 2, because the edge abundance of the edge coming in is 2, and the total outgoing abundance is also 2. So you add them up, and that invariant should hold at every node in the weighted DeBruijn graph. However, there are a lot of nodes in the graph where you need some extra information to actually enforce this invariant. And those nodes are the ones that appear at the start or the end of reads. So for example, in this case, you can see the node again labeled with AAAA. There are 2 reads coming in. So the total incoming abundance is 2, but there's only 1 read going out. So the outgoing abundance is only 1. However, if you record that how many times that node appears at the start or the end of any of the reads, you can use that information to actually enforce this invariant. So this node appears at the end of a read once, so you can use that information to actually enforce the invariant. So
if a node is at the start of one read and at the end of another, so it's 1, 1, you can get away with skipping that, right? Because it doesn't violate the invariant.
So yeah, I mean, so there are 3 kinds of nodes in the actual graph. There's a node which appear at the start, there are node which appear at the end, and then as you said, that it could so connect like 2 reads together, and it can glue 2 reads together. And there could also be cases in the actual graph where an edge leaves the node and also comes in the node as well, because it can have a loop of itself. Like for example, if a node is there like AAAA, and then if there's another node, if you just go to the left, if you append an A, you will again come back and so on. So there are a lot of corner cases in the actual implementation that we dealt with. But on a high level, like if you just store this amount of extra information, that how many times given a node appears at the start and the end of a read, you can enforce this invariant on all the nodes in your graph. So here is the representation of the weighted DeBruijn graph in our system, which is debugger. So the graph is there, and we have 3 data structures. The one on the far left is the abundance data structure, and in which we actually store the abundance of each and every edge in your input data set or in your graph. And these 2 data structures on the right, as I told you before, that these actually store the information about how many times a given node appears at the start or the end of the reads. So these 2, the right 2 data structure are exact data structure, they're not approximate. And the one on the far left is actually an approximate data structure, which is a counting filter data structure. And the size of the data structure on the right is again very small, because given the actual amount of data set, the number of reads in the data set is very small, and it accounts for like 10 to 20% of the overall data set size. So the one on the left is the actual data structure, which is very, very huge. And the other 2 on the right are very small data structure, even though they're exact. Now, let's see how the invariant works and how do we actually do the error correction in the graph. So as I told before, the one on the left is an approximate one, so they could be errors. And in this graph, there are 2 kinds of errors. The one on the top is an edge CCGTA. That edge doesn't appear in the input data set, but it appears in the counting filter because of the false positives in the data structure. And so that's an edge. It's a new edge, and it's a topological error in the graph. And we have another error wherein the weight or the abundance of a given edge, which do exist in the graph, like appears to be an overcount. So we have an abundance error as well. So we have 2 errors in this graph, and we'll see now how do we fix all these errors. So the algorithm is very simple. What we do is that we go to every node and try to enforce the DeBruijn graph, so weighted DeBruijn graph invariant. And if the invariant doesn't hold, and if we can change a single thing in the graph that can fix the invariant, then we do that and we go ahead. However, there could be cases in which there could be multiple ways to modify the graph in which we can enforce the invariant. And in that case, what we do is that we go to nearby nodes, learn more information about the graph, and then we come back so that there must be only one way to modify the graph to actually enforce the invariant on that node. So let's try to fix the errors in this graph. So let's first pick that node on the far left. You can see the invariant doesn't hold here because the incoming abundance is 0 and the outgoing abundance is 1, so it doesn't hold. So even if we use extra information, that is the number of times it appears at the start or the end of reads, it's still 0. So we know that there's only one way to fix that, to fix the graph or to modify the graph to actually enforce the invariant. And the way is that the total outgoing abundance should also be 0. And so if we do that, if we reduce the abundance of that edge, then we can fix this, we can enforce this invariant. And now you know that the weight or the abundance of that edge is actually 0 and not 1. And so you can fix these like topological errors in the graph. Now let's try to enforce this invariant on this node. And you can see the invariant doesn't hold because incoming abundance is 2 and the outgoing abundance is 3. 2 plus 1, the abundance of the outgoing edges is 3. However, now to fix this, we can modify the graph in 2 ways. We can either decrease the abundance of this edge by 1. In that case, the invariant will hold. Or we can also decrease decrement the abundance of this edge by 1, and the invariant will still hold. So there are 2 ways to modify the graph, and we don't know which way is the correct way.
And you're not allowed to increase the one on the left to a 3 because the counting balloon filter can only overcount?
Yes, so you can only decrement. The error is always one-sided, so you can always decrease the, So here we don't know enough information how to modify the graph. So what we do is that we go to neighboring edges and we learn more information. So we go to this edge and try to enforce the invariant. And you can see the incoming abundance is 0, but this node appears twice at the start of reads, and the outgoing abundance is 2. So we don't need to do anything in the graph to actually enforce the invariant because invariance holds here. But we learned the information that the weight or the abundance of this edge is actually correct because we didn't have to do anything. Now we go to this node and try to enforce the invariant, and you can see here the incoming abundance is 1, outgoing abundance is 0, but this node appears once at the end of a read. So again, we don't have to do anything. The invariant holds here, and so we get this information that the weight of the neighboring edge is also correct. Now we can go back to this node and try to again modify.
So you only know that's correct after examining all possible incoming nodes,
all possible incoming
and find
edges,
that there are
all the neighbors,
Okay.
And so if we go back now to this node and try to modify the graph again, and now we know that there are 3 edges involved in this equation, and 2 of them we know that their abundance is correct. So there's only one way to fix the graph, and we do that, and we can fix basically all the errors in the graph by using the simple invariant. The algorithm here is a standard work queue algorithm where we bootstrap the algorithm with a set of C edges for which we know the abundance is correct. And then we try to expand this set by going to each and every node and trying to enforce the invariant. And if we can fix the graph in only a single way, we do that and we move on, so on. We have a proof in the paper that this algorithm is close to linear time algorithm, like it is n times log n over log 1 over 4 epsilon, where epsilon is the error rate of the underlying counting filter data structure. So the amount of guarantees or the amount of space you might end up doing depends on the error rate of the data structure. Let's quickly take a look at some of the results. So we did some experiments and we took 4 different data sets in computational biology, and all of these data sets had a few billion distinct k-mers as the input. So all these k-mers will act as edges in the graph. And we try to compare our system with other approximate and exact weighted DeBruijn graph representations. So approximate weighted DeBruijn graph representation, state of the art in that is Squeaker, which uses another counting filter data structure. And the Squeaker exact is exact representation of that of a weighted DeBruijn graph, and it uses a hash table to do that. And you can see in this graph on the x-axis we have 4 different data sets, and on the y-axis we have the space usage in terms of number of bits per k-mer needed by the system or the representation. So since the y-axis is space, lower is better. You can see for all the different data set, debugger being exact takes almost half of the space compared to state-of-the-art other exact representation. And compared to the approximate one, it takes some extra space, and that extra space is 18 to 28% for all different data sets. However, when you talk about the accuracy, you can see that the errors in both Squeaker exact and debugger is 0 because they're both exact. However, the number of errors in Squeaker is very large. It's of the order of millions. So even though debugger takes only 18 to 28% extra space compared to Squeaker, but there are no errors in debugger, and we fix all these errors using the simple error correction algorithm in the graph. So to conclude, one thing to note here is that, as I told you before in the talk, that storing this extra information in the graph in terms of the weights or the abundance is an obligation, but it's also an advantage because now we can use that extra abundance information to give higher guarantees on the graph structure and actually fix all those errors in the graph using only the weight information in the underlying data set. And the last point, which could be more interesting to you guys, is that now we have started looking into other graphs in different fields, like product graph in Amazon and some other graphs as well. And we are trying to see actually exploit some domain-specific information, those graphs, to actually represent them approximately and in a very small amount of space, and still fix all those errors in the graph. The code for this system is available open source at GitHub. You can guys go and give it a shot. And thanks.
All right, well, thanks. So questions?
Yeah, so that algorithm that was, you said the runtime was ed log n over log 1 over epsilon. Yeah. What's the space usage of that?
Like you mean the runtime space usage?
Yeah.
Oh, okay. So it is pretty much. I mean, we don't need any extra space during the runtime. So because we maintain this set of C edges, and we can use that when you have this graph, you already have a set of the actual number of edges, right?
Yeah.
So what we do is that we traverse this graph, go to each and every node, and we try to enforce this invariant on each and every node. And if the invariant doesn't hold, we know that there's something wrong nearby in this node. So what we do is that we have some WHP bound in the paper actually. So at a node, if the invariant doesn't hold, we go to d-hops from that particular node and insert all those edges in a separate set and say that the abundance of any of these edges can be wrong with high probability. And so we only so when you traverse this whole graph, the number of nodes actually where the invariant doesn't hold is a property of the amount of error in your actual data structure. So that is a factor of your epsilon here.
So maybe let me ask another couple ways. What's n there?
N is the number of distinct edges in your graph.
Okay. So what's the output of this error correction algorithm?
So the output is that, so here, so you can see that in this representation, you have the abundance data structure, right? And this abundance data structure can only result in an overcount. So at the end, we store this small exact data structure that only store the deltas for any edge that has a wrong count in the actual abundance data structure. And so what we do is that now if you query for any particular edge in the representation, you first find the abundance in the actual data structure, and then find if that k-mer or the edge is also present in the final error correction data structure. And if there is some abundance in that, then you subtract that abundance from the abundance given by this data structure.
Yeah. So I guess what I'm having trouble understanding is, well, it seems like the output of this algorithm is sounds like that's maybe sort of like what Squeaker is.
No. Okay.
Anyone understand the
That's
question?
that's a highlighter. Those are.
Oh. Okay. So you have an edge here and the abundance here.
Right.
And if you have only this structure, which is an approximate data structure, then this only thing is Squeaker. Because Squeaker is approximate representation.
Or Squeaker exact.
Okay, Squeaker exact is exact hash table. It's an exact hash table. Like you can use any hash table if you want. And that's exact, that is Squeaker exact, but hash tables take a lot of space. Now, in DeBruijn, what we have is, so we have these small representations like the ones there that store the count for the number of time any node appears at the start and the end of the, which is a small amount of information. But when you run this error correction algorithm on this representation, then it outputs another exact data structure, which is the hash table again. What it does is that if there is an edge like A, C, T here, and the abundance is 4 here, but when you did this error correction and you found out that the actual abundance is not 4, but it is 3, because you have to so decrement somewhere. So it will have a key here with the same edge, and it will have 1 here, or -1 exact actually. So now when you return any the weight of any particular k-mer, you query here first, and it will give you 4, and then you query for that thing here, and if it is here, then you take the weight and add them up together.
Yeah, so let me
Yeah.
try again. So why don't you just store this entire thing as your compressed format? What's the usage of the somewhat smaller format that's really difficult to query?
Compress in the sense like what, you take another exact hash table and then compress it, or
Well, so
how do you compress it? Because if you just use the exact hash table,
no, so just store everything that you've written on the board there
yeah, okay, all these things
as your data structure.
as one data structure.
Well, that's your representation of the graph.
Yeah, this is our representation of the graph.
I think
But
that
the-
is the representation of the graph, Warren.
This is the one.
Okay, so
So this is what debugger is.
The thing is that left piece, because it's something based on like a Bloom filter type
Yeah.
thing, those things aren't an explicit table. They're sort of
yeah, I know
implicit.
that.
Okay.
So you basically store like the Bloom filter and all the errors of the Bloom filter.
Exactly.
Okay, so
Yeah, so these are all the errors basically, like whatever the errors you found out during your error correction algorithm. This is the approximate representation. So basically all you need is like this structure and this. This you need like during like error correction, but you don't need it later on. Once you have found this table, then you don't need these tables actually. So you just need like this and the errors in the whole graph.
okay, so the sizes you're reporting are after this
Yes, so
after this
size-
process.
The size I reported in the benchmark is actually everything. So it is actually the size you need during the construction as well. So we don't report the final size, but the final size will actually be even smaller than what is here. Because at the end, once you have done this algorithm, you don't need these two things.
Okay.
And one more thing I want to point out as because you asked this question. So in the paper, if you read, there are two different algorithms there. One is global like error correction, one is local error correction. So global means once you have created this structure, you can traverse through the whole graph in one phase and do all corrections and store this structure there, and you will be done. Then you don't need error correction later on. However, if you don't want to spend that much amount of time to do all the like error correction beforehand, so what you can do is that you can do the like error correction on the fly as well. On the fly means you just keep this and these two, and you query for a given keyword. And when you query, you actually just, instead of like returning the abundance from here, you try to enforce the invariant on that particular nodes adjacent to that edge. And if invariant holds, then you know that the abundance is actually correct. But if the invariant doesn't hold, then you can go look around nearby, fix the errors there itself. Because this error correction algorithm is very local. You don't have to know everything about the graph. You have to know only about your neighbors. So you can do that thing on the fly and return the abundance back. And if you do that on the fly, the error, like the runtime for that would, so right now the runtime is n times log n over log of 1/4 epsilon. That's when you do it for all the edges in the graph. But if you want to do it only for one, then this will be uquery time, actually, when you do for locally one particular edge only. And that still is very fast. And the most of the cases, you don't have to do any error correction because this thing is very small usually. And for our data set, this thing was like 0.001, something like that. The error was very, very small in the data structure. So the number of this size of this data structure is very small as well.
So question, so I understand if you're starting at a point you can sort of walk, then that's a way of discovering errors. But if you have these disconnected components, are you just doing an exhaustive search over all 4 to the k k-mers to see if they're in your, like there's no way of just looking at your Bloom filter and figuring out what are the false positives, right?
Just by looking at the structure, no, yeah.
Right, so you have to query it to see, is this in there?
Yeah.
Right, and so are you doing just some exhaustive search over?
No, so for example, you are saying for this kind of
like how would you find CCGTA if
is
that
an error
was
or not? Yeah, because so what you do is that you have CCGTA, and when you query for this, what
how do you know to query for it?
How do you know to query for it?
Yes, so you might know some node and you can traverse. I understand that. How do you discover edges that are in your approximate data structure that shouldn't be there? How do you even know to query for them?
Because of the start nodes,
You
right?
just query for them first of all, You just query for.
Are you looking at all 4 to the 5th combinations in this case?
No, you just query for only this particular k-mer in this data structure, and this data structure is going to say yes, it is there.
I'm asking, how did you choose that k-mer to query for?
Oh, okay. The queries will come from some application, whosoever wants to use this representation. So there could be many applications that use this as an underlying representation, and they want to do queries for random k-mers.
That's fine for the on-the-fly one, but you said you're doing global error correction. So if you're doing global error correction, you need to sort of found them all first, right?
Yes. So
okay.
No, I mean, you don't have to find them all. What you have is that for the global, once you construct the system, you have only this thing available to you.
Yep.
And you can start with a seed k-mer. So you need the seed k-mer here, right? But you don't need exactly because you already have the seed nodes, because these structures are already exact. So we use these structures to actually start our search.
So you started every seed.
Okay,
Yeah.
so you started every seed,
to expand this the whole graph, because we already have the seed, because we have these auxiliary structures. If you don't have these, then you actually need one k-mer from each connected component in your graph to start your whatever exploration of the graph, and then go ahead doing that.
Okay.
And this kind of a use case is a different one, because what people do in many different applications is that they take all of this data, they represent it as a DeBruijn graph or a weighted DeBruijn graph. And what they want to do is that they have queries in the form of a read. So what they have is I will give you a read, and I will want you to tell me if this read is there anywhere in this whole graph, and you want to match that path. So you again take that read, chop it off into k-mers, and then you query for each k-mer in the graph. So that is a random query. And in that case, we do this kind of an algorithm to fix those kind of things. So there's multiple different applications for this representation.
So, I really liked your talk, and I was wondering what kind of invariance you had thought about as interesting for like this graph has a really great property that the in degree is equal to the out degree or something, right? So you can always kind of exploit that. If I think about like Twitter, the in followers are not always equal to the out followers, and I'm wondering, if you could use like distributional invariance, like most users aren't popular, so if you get 1,000 edges coming into Brian, something's totally wrong, but Justin Bieber, maybe it's okay. Like, on most users, don't have many edges, stuff like that. So like actually take advantage of the power law distribution.
Yes, something like so. Even in this work, when we started off, we didn't really realize this kind of an invariant initially. So what we were doing is that we were using some brute force kind of techniques, because when you have this graph, so like when you walk along a path in the graph, say for example this, and then you have a fork. So all of these edges have some abundances attached to them. And since you know that these this whole non-branching path is actually coming from a part of the actual genome, so the abundance of all the edges on a given path should be same or like very close to each other. Because they're coming from the same part of the genome. And when the instrument reads, they will read it the same amount of numbness or some number of times as for every edge. However, as soon as you go on a fork, then now you don't know which path is the correct path here. So what you do is that you find out the coefficient of invariance on this path. And when you're here and you want to find out if this is the right path or this is the right path, you go ahead like 3 to 4 hops on both the paths, find out the weight variation on both the paths, and only so one of them is going to be close to this path, actual path, and the other one is going to be like different. And so we use those kind of like heuristics to actually find out all the error correction in the graph as well. So and the graphs for like many like RNA assemblies are very complicated, because you can have multiple paths in between 2 different nodes. And now you do not know which path is the actual correct path between these 2 nodes. Like now you do that, like you find out the abundance of all the paths, and then do some analysis, so which is the correct path here. And so
and can you like you're like fitting a t-test to it or something, saying this is like the most likely to be
something like that. But for all those cases, you need some domain specific information. How the thing's going to look like. And the similar thing is for like Amazon graphs as well. Like if you have a graph of all the products and just between them if they were in a cart together, then if you have a laptop and you have say a screen guard for the laptop, and the number of times these two products were in a cart like together will be very high compared to a laptop and a baseball bat, say. And if so this is your actual graph, and you can have this false edge in your graph because of the underlying data structure. And so if you find out the weight here and you find out the weight here, then you can say that all the neighboring edges of this particular product have a weight which is very high, but only this edge has a weight which is like different. So if you calculate the weights of all the neighboring edges, and you can weed out all the one which is odd there.
Okay.
Something like that.
And do you think you can have any like results about like, you know, if your edge distribution looks like this, then you
Yes.
can definitely find the bad ones, like
Yes, something like that.
Okay, yeah, I'd be interested to read that paper.
Okay.
You know? So please write it.
Yeah, I mean, we're looking into those graphs now, so it will take some time, but definitely.
Any other questions? All right, well, thanks, Prashant, again.